Okay, hi everyone. My name's Emma and I'm an undergrad at Stanford and I work with Keith. And together we were working on a tool called WasmBounds. And WasmBounds tries to eliminate memory bounds checks with abstract interpretation. And this is still a very work in progress project. So to provide some background to convince why we need a tool to eliminate memory bounds checks, in Wasm 1.0, out-of-bounds accesses were pretty efficiently caught with the hardware guard pages, but with 64-bit memory and single-byte page sizes, and in some embedded environments, these hardware guard pages aren't necessarily available or efficiently implemented. And so software bounds checking is often used at a cost, or sometimes no bounds checking at all, which doesn't get you the safety guarantees. So it'd be nice to be able to, delete some of the bounds checks with analysis. So the insight that we had was that we already know that some accesses are safe. For example, in these languages, bounds check, the accesses to container types are already bounds checked. So these accesses are getting bounds checked multiple times, and it'd be nice to recover that information. So it's clear at the source level usually that certain accesses are safe. For example, in this toy program in C, the dot product function is accessing the two arrays, and it does so via helper functions that we know are safe. Same for the other languages I showed. We know that the compiler is inserting bounds checks into the container accesses, but then when you compile this program into Wasm, it's not obvious that the two I32 loads are safe in this WAT. And so the idea is to use abstract interpretation to over-approximate the addresses and then eliminate the bounds check if we can prove that the access is safe. So a little bit of background on abstract interpretation. Basically, the process is we want to translate each Wasm instruction to operate over an abstract domain. And then we'll run the program through the interpreter multiple times until the abstract store reaches a fixed point. So to break that down, the abstract domain that I landed on is the strided sign agnostic integer interval. So what that means is you might have a concrete set of some numbers 0, 4, 8, 12, and then the interval would just be the lower and upper bound 0 and 12 with a stride 4 in this case to increase the precision and granularity. And then sign agnostic just is something that I had to add because of the fact that Wasm I32s are not necessarily signed or unsigned. So it's just wraparound logic for that. So yeah, I think it's helpful to walk through how this abstract interpretation actually looks in the toy dot product program. Before I get started doing that, this program has two locals, the result and the offset of the dot product. So it initializes the result local to be 0 and the offset local to be negative 4096. Then there's a loop. In each iteration of the loop, we use the offset to get two areas in memory and multiply the value and increment result. And then in each loop iteration, we also increment offset by 4 until offset becomes 0, and then we escape the loop. So for the abstract interpretation, the first round represents what are the possible values of offset and result when there's only one loop iteration. So at the top of the loop, we know that offset is negative 4096, the constant value, and that's represented by a stride of 0 and then a lower and upper bound of negative 4096. And then we also know that result is 0. And then after we go through the getting two elements of the array and multiplying them together and incrementing result, we update result to be top or an ambiguous value, because to over approximate we just assume that everything in memory is like unknown. And then when we increment offset by 4, then the interval updates to be like the constant value of negative 4092. And then what happens after when we hit the BRIF is that the BRIF, so the abstract interpreter knows that the BRIF's condition is on offset. So it's checking if offset is 0. And to fall through outside of the loop, we know that offset has to be 0. And then the backwards edge, offset can't be 0. So the abstract interpreter like notes down that at the end, at the outside of the loop, offset is bottom, because in the before the BRIF, there was no 0 in the interval. So we get like the empty set when we intersect with 0, and then bottom means like the program point is not reachable. And then for the backwards edge, we have to join whatever is not 0 from before BRIF with what was offset before at the top of the loop. So if you remove 0 from negative 4092, it's still negative 4092. And then if you join negative 4096 with negative 4092, you get this interval with stride of 4, because you can be either negative 4096 or negative 4092 during the second iteration of the loop. And then notice that result is also top, because when you union like top with anything else, you still don't know anymore about the value that it could be. So then the next thing that the interpreter does is it does a widening. And basically what that means is we observed that the upper bound grew like clockwise in the ring. And so we know that we can estimate that maybe the upper bound will continue to grow. And so there are some thresholds that we have. Basically, they're just static values that like you scoop out of the program, and then you pick the next value like going up. So in this case, we were at negative 4096 to negative 4092, but the next threshold is negative 1. So we just estimate like maybe it goes all the way up to negative 1. And if that's the case, we'll reach the fixed point faster. If not, then we won't reach the fixed point. So it's still a conservative estimate. Then after we do the widening, we can just canonicalize the interval just down to negative 4. Basically what that means is like before when we had negative 1, that's not actually, negative 1 is not reachable with the stride of 4 because it's not a multiple of 4. So we just lower it to that next actual value in the concrete set. And then we can propagate that through the program. When we add 4 to the offset interval, it just means adding 4 to the lower and the upper bound. And then doing the same thing with like figuring out what interval is falling through out of the loop and what interval is going back to the start of the loop. So for the fall through, if you intersect negative 4092 to 0 with 0, you get like the constant value 0. So we know that at the end of the loop, then offset is definitely 0. And then when we go for the backwards edge, we know that if you remove 0 from negative 4092 to 0, then you get the same interval that we had before, negative 4096 to negative 4. So if you run through this one more time, then you're like, oh, the entire store is the same, so we've reached a fixed point. And so this is kind of an intuition for how abstract interpretation would like end up recovering the interval that like the values in the abstract store can actually take on after arbitrary amount of iterations. So this is kind of a backwards talk to talk about the architecture after running through it, but basically it just takes in Wasm binary. It's agnostic to the language that the source program was written in, and we parse the Wasm binary into a control flow graph, partially with Wasm parser. And then the control flow graph is what actually gets fed into the abstract interpreter, which has the abstract store that we're keeping track of, and then this like transfer layer to abstract domain situation. So the transfer layer is the part that is actually translating Wasm down to whatever the equivalent would be over the abstract domain, and then I have some abstract library that I wrote to use. And then we have a fixed point engine that kind of runs the interpreter until the fixed point is detected, and then the output is some instruction offsets to safe accesses that can be passed to any Wasm runtime, and then you would just know that those instruction offsets don't need to be bounds checked. So I think what I was asking myself as I was making this interpreter is, how can we trust, how trustworthy is it, and what's the major danger here? And I think what it is like, you don't want any false positives. You definitely don't want to say that a load is safe, even if it's not. And so there are two strategies that I've been thinking about to address this uncertainty. The first is to verify the soundness of the domain with Verus, and then the second is to make the transfer layer infer the Wasm semantics from the spec. So yeah, this is similar and inspired from what Mikhail and Ben are doing with canonical bytecode definitions, and also conversations Keith and I had about spec tech earlier in the year. And these verification strategies target this part of the architecture inside the abstract interpreter. So what does soundness of the abstract domain actually mean? Basically, in this context, I just mean like the operations on the abstract intervals over approximate the operation on the actual concrete set. So if you had two intervals, A and B, then adding them abstractly should be like actually adding every single element in the concrete set should be a subset of what the abstract add does. And then for meet, it should be related to the intersection, and join as the union implies that the one concrete set is a subset of the other concrete set. So how do we use Verus? Well, Verus is a Rust-based SMT verification tool. Basically, what it lets you do is, I wrote my whole abstract domain in Rust. So I would have a function like join, it's an impl of like the interval, and it takes in another interval, and then it joins them and it gives you the result. And what Verus lets you do is it lets you specify pre and post conditions on this function. So it's saying like, if the preconditions are satisfied, then Verus can attest to the fact that like the post conditions will definitely be satisfied based on this implementation. So in this case, the preconditions are not as interesting. WF is just like some well-formedness property of the interval, but the post condition is where it gets interesting. We see like there's this quantifier for all Rust U32s. If the value, if that value is in self or in joinee, then the resulting from joining the two will definitely contain that value as well. And so basically we're just encoding like the meaning of these abstract operations into Verus, and then I was able to get everything to verify that indeed the abstract library is sound. And the second strategy I've been thinking about is extracting the ground truth out of spec tech. So in this example, like according to the spec, i32.add just, it pops two things off the stack, and then it adds them and then pushes back onto the stack. And I think what I would want is to extract all of this information out of the spec tech, replace iadd with abstract i32add, and then not have to hard code that information in. So far I've basically just like naively parsed the spec tech, but I want to work more on like the interfacing with the AST. So I think the takeaway is that abstract interpretation is a viable method for recovering safe accesses, but I guess I think this is work in progress in the sense that we haven't tested it on like a diverse amount of Wasm programs, and I think that there are some assumptions made in this presentation about like this Wasm function being a pure function and how to deal with parameters and stuff like that. So still thinking about these types of things and how applicable that will be. And then the second takeaway from my verification interlude is I think that using different strategies to verify this interpreter is necessary. And like if you really formally wanted to verify this interpreter, you might write the whole thing in Verus, but that's just not feasible for some like production level tools. So I think it is interesting how because Wasm is well specified, we can like use different tools to verify the Wasm toolchain. Yeah, that's my whole talk. Thanks.
Awesome, thank you. We got a couple questions in the room.
I had a question about the threshold thing. I guess how do you come up with that set of threshold values? I think it was like minus 4096, which I assume is just kind of your starting value, but then minus 101. Why is it okay to just skip straight to minus one? Yeah. I mean, like, and would those thresholds be different based on whatever operations you're analyzing?
So the thresholds are like literally taking out every single numerical constant in the program, and also including the like U32 max. And basically, I think so. It's okay if you don't get the widening correct the first time, which is why the thresholds are just like whatever numbers you can come up with from the program that you think are suitable guesses would work. Because if you didn't get the guess correct, then you would just like everything would converge onto concretely interpreting the program like step by step, if that makes sense. So the widening is just to like get performance gain from the naive method of like literally going through all 4096 iterations.
So Thomas first.
Thanks. This is really cool work. We're actually currently doing something similar for WasmGC in binarian. So I have a colleague working on what's basically an abstract interpretation using a different abstract domain, so not using intervals. Have you considered any other abstract domains and sort of compared them? I know there's a lot of literature on eliminating bounds checks with various domains.
Yeah, it definitely took a few iterations to get to this like sassy interval that I found some papers on. But I haven't thought too much outside of intervals. Like naively, I started the whole project out with sets, and I like literally went through the whole program with every single iteration. And then I was like, okay, clearly I need an interval, but the problem is that Wasm is like not signed or unsigned. So then I got sign agnostic. Then I was like, oh, for iterations where you have constant, like something is incrementing every single iteration, then the stride is really helpful to get finer granularity. So I think my insights on the abstract domain is like you have to test it on actual programs to see what works.
Makes sense. And then one other note is we've also had good luck using fuzzing to verify that our lattices for our abstract domains are actual lattices. So we just sort of like generate random elements and like check all the lattice properties on them, which obviously is not as nice as having a proof, but doesn't require crazy, proof systems either. So maybe worth looking into.